Welcome to the Sedona Community Office Hour of September. So as usual, let's briefly introduce some background information about Sedona. So Sedona is the most popular open source cluster computing engine for processing big geospatial data. We have our website, sedona.apache.org. We also have our GitHub account under the Apache Software Foundation. We have our social media account. You can find us on X as Apache Sedona. You can also find us on LinkedIn as Apache Sedona. And so Sedona is a project we started about 10 years ago. So far, Sedona is being used by many companies in production across different industry sectors. As you can see here, so our Sedona users and contributors coming from also different areas, including logistics such as GB Hunt and telecom company like T-Mobile, Zillow, and so on and so forth. So far, the overall downloads of Sedona has exceeded 15 millions. The monthly downloads of Sedona has exceeded 2 millions per month. And we have over 140 GitHub contributors. So if you guys are interested, you can always participate in the Sedona community and contribute back to the software. Here is a diagram about the Sedona ecosystem. So as you can see from your right, Sedona has mainly three layers: spatial query processing layer, spatial dataset layer, and also distributed engine layer. So the query processing layer, which is on top, so it has many different programming languages, such as Spatial SQL, Python, Scala, Java, and R. So as user, you can always interact with Sedona with one of the languages here. And this layer also integrates with a number of developer tools, including Jupyter Notebook, GeoPandas, RStudio, and Tableau, Apache Zeppelin. This layer also equipped with a number of distributed query algorithms. So basically, given spatial SQL query, Sedona will take this query and translate that to a query plan and execute this query across machines in the cluster. In this layer, we also have a spatial query optimizer that takes a spatial query and automatically figure out what's the best query algorithm should be used for this particular query. The second layer is the distributed spatial dataset layer. So this layer has lots of cool technologies that actually manage how the data is organized in a cluster. That includes spatial data partitioning, spatial indexing, and spatial data serializer. This layer also works with batch data processing as well as stream data processing. The bottom layer, as I mentioned before, is a distributed engine. Sedona can run on top of different query engine, so it can run on top of Apache Spark for batch processing and the Snowflake as well. And it also works with Apache Flink for stream data processing. And if you are using Snowflake, so there is a plugin in the Snowflake marketplace called Sedona Snow, which is the basically it's a binary of Sedona Snowflake. And by far among this engine, so Sedona's the spatial support we have on Apache Spark is the most comprehensive one. So the easiest way to get started with Sedona, like today, like immediately, is to use Sedona's Docker image. We have our Docker image hosted on the official Apache Software Foundation on Docker Hub. You can always pull Docker image like this. So you can pull a Sedona Docker image by specifying a specific version. You can always start a Sedona Docker image using the Docker run command. So this will actually give you a Docker image that's run a Jupyter notebook and a Zeppelin notebook. In those two notebook environment, which opens up your one of your browser page, you can actually run Python program there. You can also on the Zeppelin notebook, you can also type in Scala and SQL and Python as well. Sedona release cadence. So Sedona follows the 3-month release cadence. We have made multiple release this year. So Sedona 171, 172 were made this year. And right now we are working on a major release 180. So we were supposed to release that last month, but it got delayed. So there is a blocking issue, which is the Apache SAS dependency. So we are looking at release Sedona 180 sometime like next week, so that this will have lots of exciting features, which I'm going to talk about later on. So in the upcoming Sedona 180 release, so I have talked about this a couple of times. Basically, there are lots of exciting features. In particular, there are some breaking changes. So Java 11, Java 17 support, and Spark 4.0 support, PipeLink, so on and so forth. So let's dive into each topic here. So first of all, Java 11 support. So in the upcoming 1.80 release, Sedona gonna be dropping Java 8 support, and will only support Java 11 and Java 17. Java 17 is for our support on Spark 4.0. For our support on Spark 3.4 and 3.5, you'll be using Java 11, as well as for Sedona Snow and Sedona Flink, we'll both use Java 11. So the reason why we are doing that is, first, we need to use the latest version of our underlying dependencies, but that includes GeoTools. We want to use the latest release of GeoTools, which is going to help us solve some security issues. And on the other hand, we also plan to use Apache SAS to deliver a better, more accurate version of ST transform. Currently, this is a blocking issue for the 1.80 release. We are still we have a snapshot release from the Apache SAS community, but we are waiting for them to make a formal release of their upcoming release 1.5. So we are working closely with the Apache SAS community, and I believe we will be able to address this next week. And also another reason is Spark 4.0 only runs on Java 17 and Java 12, 21. So here is the impact. So we actually expect actually very minimal impact on our customers if you are using one of the major Spark hosting service on the cloud. So basically, right now, all major Spark hosting service has at least one LTS version on Java 11. That includes Databricks, AWS Glue, and AWS EMR. So if you use AWS Glue, right? I believe later, I believe early this year, so Glue released 5.0. So it's Glue 5.0 actually introduced Java 17 support. You'll be able to actually run Sedona on that as well. And Snowflake, which is the one for Sedona Snow, has been using Java 11 a few years back, and Flink 2.0 defaults to Java 17. So based on all the statistics we have here, we could expect this have very minimal impact on the users. And another exciting feature in the upcoming 1.8 release is the better ST transform. Many of you have been using ST transform in Sedona, right? So it is a widely used function. So what it does is it takes geometry and the EPSG source code and the target code. Basically, it reprojects coordinates of the input geometry from the source CIS to the target CIS, right? So this usually gets you a better, more accurate coordinate, which adapt to your local CIS. So in the past, this function used library called GeoTools, right? And unfortunately, so the logic implemented in GeoTools is now is not well maintained. So the maintainers haven't been updating the logic there for a while. And we want to have more accurate implementation of ST transform that actually have good impact if you want to have high precision of your spatial relationship calculation. So we actually plan to use Apache SAS to deliver ST transform that allows you to specify grid files and error entries to deliver high precision ST transform, right? And we expect the overall performance going to be similar compared to the GeoTools based ST transform, but it just give you better accuracy. And the ST transform by nature is a very complicated function because it is going to be very computationally intensive if you want to transform a large data set from one series to another, right? It has lots of complex data shift. So that's why we need to use an external library for that. Cool. Another very important update in the upcoming 1.8 release is our geography operator, right? So in the past, Sedona has been supporting geometry calculation and geometry data type for many years. However, it does not have geography data and operator support. So basically, when we talk about geography data type and geography operators, we mean the spheroidal distance calculation and geodesic distance calculation, right? And in particular, we need to make sure we want to support this kind of spatial relationship over spherical surface. And we also want to support cross anti-meridian geometries and also geometries close to, to the two poles. So currently, we have sort of geography support through our geometry data type. But these are all workaround. So we expect the latest geography data type and operator support is going to be able to deliver better experience and more accuracy. So currently, if you use Sedona geometry, you actually can have spheral distance calculation in ST-DVZ, ST-buffer, and the ST-distance sphere and the ST-distance spheroid. So this will work, right? But there are issues around these functions, right? So most of them actually right now, if you use this spheral distance calculation, it only work with point data. So if you give non-point data such as polygon, right? It's going to take its centroid and only measure distance based on the centroid. So we're going to fix that through our geography data type for that. So the geography data type actually was added a while back in Sedona 171. However, it is just there as a placeholder and does not have any corresponding operators. In Sedona 180, we're going to introduce a number of geography operators on our existing geography data type. It's going to be implemented based on the Google S2 spherical Earth model, and we have actually finished our Java-based geography library called S2 Geography inside Sedona. So if you're interested, you can actually already find the source code that have been merged into the master branch of Sedona. And it's going to introduce a number of a number of OGC simple feature operators, as known as the ST functions on the geography data type. We have added a number of those operators inside Sedona right now, and this is going to require lots of more effort on the on this geography data type. So we're going to continue working on that through the 1.8 release, like 1.0, 180, 181, and 182 possibly. And recently, so another interesting library. So this is actually done by the company I work for, Variables, right? We recently released a library called well-known location. So if you are using Sedona in the past, you probably have a hard time looking for polygon boundaries of state and country, and also maybe cities, right? So we recently released this library called well-known locations, in short WKLs, right? So you can find it on GitHub. It is open source. It is free to use, right? It is a really great helper tools that help you to quickly uh, find the polygon shape of a area interest. Cool. Let's move on. So another really interesting functions we have in Sedona is the GeoPandas API on Sedona. And for that, I'm gonna invite Apache Sedona contributor Peter, who made lots of contribution on this function. And he's gonna talk about how he designed the GeoPandas API on Sedona and how that looks like overall. Peter, I'm gonna promote you to the panelist, and then you can take over. Hey, Peter, feel free to share screen.
Yeah, so just a little intro on me. I'm Peter Nguyen. I've been like the main one kind of like contributing to this big effort for giving Sedona a GeoPandas API. So just to start, about a bit of motivation about why we did this for the Apache Sedona project. Like there's these two different worlds where like Apache Sedona is built on Spark, it's very distributed and scalable, but it's very like it's like Java native. It's pretty complicated. I find it very verbose. Tons of configs and stuff. But and then there's also GeoPandas, which has been like in reality a more popular projects. Single node. It's very Pythonic, very similar to pandas. And so we thought like the two pros of both sides of these really don't need to be like independent. We can like kind of use them both together. So that's kind of what the point of what the GeoPandas API in Sedona is. It's supposed to be both scalable and distributed because it's built on top of Apache Sedona, but it's also going to be a lot more easier and intuitive, more Pythonic for us who are a little more familiar with that. Yeah, so just a little motivation, or sorry, not motivation, just a little about just what it looked like building it out. Um, so just because like Sedona is already built on top of Spark, there actually is already a PySpark on Pandas API. So we were able to leverage that pretty well. Um, so my general approach for that was kind of like inherit from PySpark Pandas as much as possible, and then building GeoPandas on top of that. Um, so that made things like pretty reasonable to do. It's like otherwise building an entire distributed geospatial Pandas API without that would be a lot more complicated. But yeah, I'm excited to show what we have as support for everything from like the geo series, the geodata frame, indexes, the spatial joins, and then everything is all like tested and documented pretty well. Um, and then just throughout the process, before I go into like the more um, important thing that you'll probably care about, I do want to highlight a bit of like the challenges of like what it looked like building this out. So for one thing, like because things are built on top of Spark, errors can be kind of like misleading, especially with lazy eval. Sometimes there'll be like bugs in upstream packages like PySpark, as well as like some that I find in Sedona that I fix myself. And then of course like other various things that you would expect like version conflicts. Yeah, so just to start, I'll go into a demo later, but just to start, I want to show a little like what it looks like internally. So this is a function here. This is called get geometry, where it's essentially just getting like the end geometry of some sort of geometry collection. And so there's all this fancy logic. I won't go through it, but essentially this is kind of like a wrapper around Sedona's st geometry n function here to like make it more Pythonic and support like negative indices. So like now, unlike Sedona, like if you just want like the last element, for example, you can write -1 instead of like like length -1 or something like that. Like, I feel like it feels a lot more natural for us Python users. Um, and then it'll also handle error handling a lot nicer. And what I mean by that is that if you don't have all this, then you will face a very scary error like this. So a lot of my work has been kind of like easing out these sorts of things. Like if you run Apache, like a negative index in Apache Sedona, you will get a very scary error like this, which the Python user, I'm like, a little intimidated and stuff. The reality of where the real meaningful error message is like right here. But without all that logic, just to demonstrate, like we'll get this massive error message that actually extends for quite a while. um, and like 6 slides of this. But yeah, all that logic is kind of just to make things a little more Pythonic and friendly. Because like GeoPandas in reality will just return none like this. Um, yeah. So before we get into the demo, I did want to highlight that with this new GeoPandas API, I feel like it opens up a lot of opportunity for like new contributors. Like if you're interested in contributing to like a top level Apache project like Apache Sedona, this provides like a very friendly um, way for you to get introduced if you're interested. Um, I'll go ahead and quickly show what I have here, but essentially that we have a good portion of the GeoPandas API implemented, but not all of it. There's still plenty of functions to implement. This thing is blocking me. I'm trying to open this. Yeah, if you're interested, I have a big little umbrella issue of like tons of other functions and implements, as well as an example PR that kind of shows you exactly um, that kind of like guides you like kind of where you need to make these changes. This one's pretty trivial. It's as simple as just calling like the corresponding function in Sedona. I feel like a lot of them will be like that. So I encourage you, if you're interested, please consider contributing. But yeah, all that being said, I'll go ahead and jump into a demo. What I have here is a cluster, what is it, like 24 machines. I was running this earlier, but essentially I'm just going to demonstrate how like seamless and like it is to like change. Um, if you already have GeoPandas code, you can usually switch it to Sedona and show kind of like what the difference is in terms of like the performance and scalability. So here's just some like important stuff in setup code. Here, what I have is I'm first going to demonstrate one little slight difference that you'll experience from like the typical GeoPandas experience, and that is that Sedona GeoPandas will be lazy. And if you're not familiar with that, that essentially just means that whenever we um, like write an operation, it's not actually going to execute and materialize until we actually need it. And the reason for that is because that allows um, Sedona and like Spark under the hood to like optimize things um, after considering the whole execution plan. Um, so for example, like if you want to read from a file and you like don't need to read all of it, like if you wait a few extra steps and like you tell Spark that you're filtering by something, then like it will decide like not to read everything it needs to. Or like if you really didn't need to perform a specific operation, then Sedona will be smart enough to like skip that if it sees that you don't need to. So yeah, I'll go ahead and run this. This is lazy as well. So this is just like we're just telling Sedona what the data source actually is. It's just setting TRS. That's not too important for here. And then here I will run this cell, and you'll notice that it's returned right away. That's because, again, this is lazy. We didn't actually perform the buffer operation here. But when we actually run it here, this is when things will actually execute because we're telling the engine that, hey, we actually want to see the results. And at that point, we're going to actually, it's going to need to actually execute it to show us what they are. Yeah, so these are some of the results here. The buffer, it computed it for everything. You'll see if you try to print that variable again, it will just remember that it was already executed. Here I have like, I'm just like picking some random numbers here to show like we really did execute like all of the like the buffer for all the geometries. It just takes a bit of time for like Sedona to like find the exact ones I did because I just picked some absolutely random ones in the list. It's not like the top or bottom or anything. Um, and then here we can execute like an area on that. So result here is a result of the buffer that was already executed. So when I run this, it's not going to recompute the buffer. Sedona is going to be smart enough to remember that I already executed that. So we just need to perform the area calculation, which is a lot cheaper. And then here, I'm just going to run the exact same code on GeoPandas. It's as simple as just changing the import. Like here, I was using our Sedona GeoPandas import, whereas here, I'm going to be using GeoPandas. So for GeoPandas, it doesn't have any sort of lazy eval. It is going to read in the entire data set. So unlike Sedona here, where like it kind of just returned instantly, GeoPandas took around like 11 seconds. This isn't too massive a data set, but like, you know, the bigger it gets, like it's going to take longer. It can be like pretty significant. Sometimes if it's large enough, like GeoPandas just won't be able to handle it, right? I'm going to get this started. Although you'll see from the last time I ran this buffer operation took 2.5 minutes-ish. So yeah, we'll be here for a while. I'll keep talking along that, but essentially we can take a look in the past and see that when we actually executed the buffer for Sedona GeoPandas, it only took 4.5 seconds. Whereas here, it's going to take a little closer to 2.5 minutes. So not all operations are going to be that significant, but like some of these like really compute heavy functions, especially buffer, are going to take a while, and that's where like Sedona GeoPandas is really going to shine because instead of executing everything on one node, it can now execute across the whole cluster, right? Yeah, so we'll just wait around for this. Later, I'll show this demo of doing a spatial join. Um,
So Peter, while we're waiting, so can you remind me how many functions we have implemented for Sedona GeoPandas?
I don't know the number off the top of my head. I want to say around like 50 plus probably.
50 plus. Yeah, that's good. That's good.
I would say we have like, I think all the predicates. I'd say like any of the ones that we don't have implemented are probably more niche and stuff for the most part. But in terms of like, you know, the operations that I'm think of the most used here, like buffer and area, your joins, like most of the core stuff has been implemented. When it comes to implementing any of the rest, it's primarily just like writing the code, but it like everything else should be fairly trivial. Yeah, that's a great opportunity for external
Sure.
contributors if they want to contribute. All right,
Thank you,
here we go.
system.
We are done. So yeah, that took 2.5 minutes. This again using GeoPandas, around 3 seconds ish. So yeah, that was to give you an idea. That was on 10 million geometries. Um, I'm gonna reduce the data set a bit for my spatial join example, or else we will be here for a little too long. So here's Sedona. Again, it's gonna be lazy. And then when we actually execute the join here, this took about 3 seconds. And then here for GeoPandas, I'm just changing the import again. Took about 4 seconds to read the data because data is a lot smaller. Except for the actual spatial join, you'll see right before I ran that took around, I think it was like 20 seconds. Let's see. Yeah, it took around 20 seconds there. Obviously, the larger the data, the larger the difference will be. And then here, in all honesty, I just threw this together like right before this without actually testing it, but I'm pretty sure what I'm going for here is that this is an example where I forgot to time this, but this was like what, maybe like less than 5 seconds. This is an example where I expect GeoPandas to just run out of memory here. Okay, there we go. At least it happened fast. Yeah, so I'd say the main pros of the Sedona GeoPandas API is that will be a lot faster for some things. More importantly, it will be able to scale much better than GeoPandas. As you can see, like, this just straight up ran out of memory. But Sedona, it will scale like massively. I've tried this on like tons more geometries. I've not run into issues with like running out of memory for Sedona, which has been great. But yeah, that was the end of my sorry, that was the end of my presentation. Sorry, it's a little late or early. Yeah, I welcome you all to try it out. Give us some feedback and consider contributing if you're interested.
All right, great. Thank you, Peter. All right, folks. Uh, some additional content before we end the office hour today. So we have released a preprint of our Apache Sedona animal book from O'Reilly. So you can always get a free copy for that. And you can search online for this name, Cloud Native Geospatial Analytics with Apache Sedona. So you'll be able to find the URL there and get a free copy of that. So if you want to learn more about Sedona, right? So this book has lots of content and talk about how to set up Sedona and how the data is organized in Sedona and how the curve processing works in Sedona in general. And as always, if you have any question for the office hour, or for Sedona, feel free to use the Q&A and leave your question there in the chat, right? And Sedona always call for help. We have notable examples. You can add your own example there. And we also have our documentation website, right? So if you have more tutorials, if you find the typos about our documentation, about the tutorial we have, feel free to create a PR on Sedona to fix those. And you can also participate in our release test. we have a voting process for each release of Sedona. This happens on our mailing list. So dev at sedona.apache.org. You can subscribe to our mailing list and get the latest update there, and you can always participate in the voting process and help us like verifying the signature of the release and try to see if there is major bugs in the release candidate. And you can also share a story with us, like uh, talk about your success story of using Sedona, like in our Sedona office hour. You can also participate in our live stream on LinkedIn, on YouTube, right? So if you're interested, so be sure to reach out to me, and you can send me an email at this email address, and we also have a Sedona Discord server, so you can find our Discord server on Sedona website. We have all the Sedona contributors, committers, and PMC members on the Discord server and answer questions for you. Cool. I think that's all for today's office hour, right? But I'm happy to stay longer. If you guys have any questions regarding Sedona, feel free to uh paste your questions in the chat. So there is a question in the Q&A. So is there any way to use spatial indices for spatial analysis and not only for partitioning? So actually, if you use Sedona Spatial SQL and the data frame API, so we actually automatically use build spatial index for spatial join. So actually, it will have index automatically. You don't have to sort of manually build index and specify index yourself. And we also have RTD API. So RTD API is the one that we have been supporting for a while, but right now we don't put lots of updates there. It is sort of like very internal API of Sedona. Uh, in that you can actually manually create spatial index, right? So you can create like R-tree and quadtree index manually in our RDD API, and you don't you could use that for our range query. You don't have to use that for spatial partition actually. So you can also build index, you can also cache index such that your range query later on on the same data gonna be gonna run faster, right? So you can do that in RDD API, and also you can explicitly call spatial partition as well in the RDD API. So basically everything is manual in the RDD API. Any other questions, guys? Okay, a question okay, from Lorena. So that's the spatial index you mean? Okay, the H3 index. Well, uh, so my suggestion is, so Sedona data frame API provide H3 functions. If you're interested, you can use that. But honestly, H3 is a compromise. is a using like spatial drawing using H3 is a compromise when you don't have spatial partition and efficient spatial processing engine. So in Sedona, we actually our spatial drawing is better than H3 index. So we don't because H3 index, as you already see, there are problems. So if you have big polygons, you're going to end up having lots of vertices, right? And also H3 index does not handle load balance. So some H3 grid might end up having lots of features. And if you do spatial drawing on that, it will actually overheat one of the machine in the cluster, and it's going to take a very long time to execute. So you can do that in Sedona in data frame API. You can do that if you want to use H3 to do spatial drawing. But the spatial drawing ST contains ST intersect in our spatial SQL API use something better than the H3 base index. It is called load balanced spatial partitioning with spatial indices. So with spatial indices like R-tree and quad-tree, and the partitioning is load balance and preserve spatial proximity as well. So if you're interested, you can use that. That one has much better performance when it comes to like large spatial drawing across point and polygon. I think I have something I can show you guys. Uh, let me. Okay. Okay, so this is an old paper we wrote years back that actually talks about the internals of Sedona, but we have way better explanation in our Apache Sedona Aurelian animal book, right? But I'm pulling this out to show you a particular figure here. Okay, this one. Okay, so this is the spatial partition mechanism I'm talking about in Apache Sedona. So we have load balanced spatial partition grid such that when you have very dense data in particular region, we're gonna have smaller grid. So the rectangle here, each of this small cell here is corresponding to a spatial partition boundary in Sedona. And you see there, so if you have dense area, you have small spatial extent to make sure basically we preserve spatial proximity. Also, on the other hand, we preserve load balance such that later on, if you have, say, pointing polygon queries, right? So if you're looking for data in Washington, so that polygon goes to the Washington partition directly. So you don't have to check irrelevant uh, data, right? And we also build local indices on each of the partition. We build R-tree on each of the small partition here so that the query is executed really fast. Cool. Yeah, let me paste this link here, right? So let me paste in the chat. Cool. There is another question. Okay, still from Miranda. So Databricks has Mosaic. Do you see it as main competitors for Sedona? Well, so most honestly, most of the spatial user on Databricks use Sedona for their spatial compute, right? And so that basically Sedona has way more functions than Databricks Mosaic. And if you probably see the Mosaic Databricks Mosaic GitHub repository, right? So don't actually maintain that very frequently. All right. Any other question? All right, guys. So if no other questions, we can stop here. And thank you all for attending the Sedona office hour today. And see you next month then. Bye, guys.